work, power, energy, efficiency. All these terms get thrown around interchangeably, but what do they mean specifically when we're talking about buildings? Though these terms seem fairly basic, it's truly important to understand their definitions when we're comparing different building systems and their different efficiency acronyms while we're trying to make these buildings an itty bit better. In today's video, we're going to go over the different definitions of these terms: work, power, energy, and efficiency. We're going to go through what the different types of systems are present in buildings, how these different systems can affect each other, and then what are some common efficiency acronyms that you'll see in these building systems. Hi there. Sorry to interrupt your program, but I just wanted to let you know, so actually I ended up separating this video into two separate videos. It ended up being way too long, so there's actually two videos. One's going to be on energy and efficiency, and then the other one is going to be specifically on the acronyms of the different systems. So once you're done with energy and efficiency, you can click over to the next video and just continue on, but I wanted to separate it because otherwise I just felt like it was way too long. Until next time, enjoy! So as we go through these definitions, I'm going to first go over work, then power, then energy, and efficiency. So Britannica defines work as the measure of energy transfer that occurs when an object is moved over a distance by an external force, at least part of which is applied in the direction of the displacement. So let's just focus on that first part. Measure of energy transfer that occurs when an object is moved over a distance by an external force. So that's pretty easy, I think, to visualize. Work occurs when something is moved over some distance. And you're probably thinking of, something physical, like maybe a person moving a box down the street. That second part of the definition is a little technical, and it's basically there just to make it technically correct. So the second part is at least part of which is applied in the direction of the displacement. And basically all that means is you need to measure in the direction that the object is displaced. But so that's basically all work is a measure of energy transfer when you are moving an object over a distance. The object can be things that we can't necessarily feel and see with our own eyes. We're also going to talk about the different forms of energy. And so with chemical energy, you have the atoms in an object or fluid. In electrical energy, you have electrons are considered an object in terms of work. And then also thermal energy are the air particles that are considered the object. So just keep that in mind, that the object is not necessarily something like a box or chair and something that we can touch. It could be also these very, very small particles. So let's define power. Power is the rate at which work is performed. Power can also be defined as the quantity of force required to cause a unit displacement. So when we first hear these two definitions of power, they sound quite different, but they do actually mean the same thing. So let's break it down a little bit. The first part is power is defined as the rate at which work is performed. So it's comparing rate to work. And now the second definition is power can also be defined as the quantity of force required to cause a unit displacement. So power is the rate that work is happening. And if you're changing that rate, that means that you have to change the force for how quickly you're going to move that object over that distance. The next definition that we're going to go over is energy. So if work is the measure of energy transfer, then energy is the capacity for doing work. And if we remember from physics in high school, we know that energy can neither be created or destroyed. As we talk about energy, I actually want to talk about quickly the 2 different states of energy and then the 6 different forms of energy. And this is probably a refresher for you, but let's just go through it quite quickly again to refresh your memory. So the 2 different states of energy are potential energy and kinetic energy. And so these probably sound familiar from when you're in school. So potential energy is the amount of energy the substance has when it's remaining in its current form, or the object has when it's remaining in its current form. Kinetic energy is the amount of energy an object has when it's changing forms. And so remember, energy can't be created or destroyed, so it's either staying put or it's changing. The 6 different forms of energy are electrical, chemical, radiant, mechanical, thermal, and nuclear. And so for each one of these different forms of energy, you have a different object. And then they change from one form to another, either using potential or kinetic energy. So let's do an example of a toy car. So in a toy car, we typically have batteries, and batteries are a chemical reaction from different substances. So if the batteries are just sitting on the counter, they have potential chemical energy. When you put them inside the car and you turn it on, the car is then converting that potential chemical energy into kinetic mechanical energy to make it move. So then you're playing with the car, it's driving all over the house, maybe your cats are chasing it, and after some time, the car is gonna get hot and it's gonna die. So then you need to plug it back into the wall to charge up the batteries again, and now you're using electrical energy to charge up the chemical energy in those batteries. So now you're using kinetic electrical energy to charge back up the chemical energy in the batteries to do it all over again. So one thing that I mentioned is that if you're using the car a whole lot, it might get hot or even warm to the touch. Same thing if you're charging it for a long time. If you really run the battery dry and you plug it in and it's been charging for an hour or 2, the car might be hot. This heat is the difference in the efficiency of this chemical reaction. Nothing can be 100% efficient. I guess there might be a couple of exceptions, but we'll put that out of this video for now. The changing forms of the energy, whether it's changing the chemical energy to the mechanical energy or the electrical to the chemical energy, it has a certain efficiency. Everything left over gets turned into heat. And that's the same for any piece of equipment or building system that you're going to consider. So let's define efficiency. Efficiency is the ratio of the useful work performed by a machine or process to the total energy expended or heat taken in. So in other words, or in terms of an equation, it's work out divided by energy in. And so simply put, it's the ratio for how much energy do you have to put into this machine or process in order to get useful work out for whatever that work the machine or process is trying to do. Everything left over from that efficiency is typically turned into heat. One thing that I do want to mention when we're talking about efficiency and energy transfer, it's important to also understand the boundaries of the system that you are considering. So even in the toy car example, we gave the example of the batteries in the car and then plugging it in and getting the electrical energy. So it kind of sounds like in that example that our boundaries was the outlet and the wheels of the car. However, we can really stretch the boundaries of our system because remember, energy can't be created or destroyed. So you can then ask the question, well, where did that electrical energy come from? It came from the power lines outside. And so where does that come from? That comes from the power plants that are converting fossil fuels into mechanical energy, into electrical energy that's then being transferred to our house, that's being put into that toy car. So that's just to say, even when you are considering a building, it's important to remember the boundaries of the systems that you're considering, because you can break everything down piece by piece in terms of energy transfer. So let's go over building systems. I separated this list into two categories. One is building systems that are typically considered when analyzing the efficiency of a building, and then other building systems that are very important but just aren't really considered when we're looking at the efficiency of a building. So we have building envelope, HVAC, which is heating, ventilation, and air conditioning of that building, electrical system, plumbing system, lighting system, building automation and control system, renewable energy or energy generation system, water treatment and distribution systems, and then a refrigeration system that may be in more of commercial and industrial applications. Then there are other systems, but that just might not be considered in building efficiency, but they are still very important. And those would be fire protection and life safety systems, elevator and escalator systems, and then communication and security systems. So through the building envelope or the exterior of the building, we're considering the heat transfer through the outside of the building, whether it's warm inside, you're trying to keep the heat inside because it's cold outside, or it's hot outside and you're trying to cool inside. Through the building envelope, you're considering the heat transfer through the exterior of the building. And so that would be through conduction. Then the next one, HVAC, heating and ventilation, you're considering the air particles through convection and keeping the inside of the building at a comfortable space for your people or whatever the space is used for. Electrical system, of course you have your electrical energy, and then energy generation, whether you have solar panels and you're using your radiant energy, or a diesel gas generator is chemical energy, or even geothermal system. You're using the thermal energy from the ground. So what are some ways that these building systems affect each other? Well, one of the examples that I like to use that a lot of people don't really realize initially is lighting affecting the interior heat of a building or an occupied space. So in typically a larger commercial office space where you do have a lot of lighting and people in the space, and you're replacing the lights with maybe fluorescent with LEDs, you're going to have net positive overall, or you will have a slight negative impact in the winter. That is typically considered when you're doing an energy analysis on this building improvement. And I do want to take the moment to say that if you don't have LEDs in your building, it's just a no-brainer. Please input LEDs in your building. Just do it. So like we said before, if something is more efficient, it gives off less heat. And so in the wintertime in your space, when you're trying to heat the space because it's cold outside, now since you put in more efficient lighting, it's actually going to give off less heat, and so your heating system needs to make up for that difference. And that is typically considered when you're doing an energy analysis on that space. Though overall, you do have a net positive for installing LED lights, but it's a small factor to consider if you do have like a natural gas system for heating the space. You will need to use a little bit more natural gas in the winter. Likewise, and something that everyone is probably more familiar with, is installing more insulation in your building envelope. When you put in more insulation, you're reducing that heat conduction transfer through the exterior walls, and now you're saving energy on your HVAC system because it doesn't have to work as hard to cool or make the inside space more comfortable. So if you found this useful, please consider subscribing to my newsletter, where I post tips and tricks and other resources to help you make buildings an itty bit better. Until next time, thanks, bye.